here we're going to kind of cut to sort of the modern age, present the modern, I shouldn't say modern, but within the last 100 years, the modern picture of the atom, which we are going to talk about the protons and the neutrons and the electrons and the shape of the atom and that kind of thing. I'm also going to present a little bit of a summary, which we did in the last lesson, about the modern view of how electrons really behave. I'll give you a spoiler alert, they're not little balls, that little hard little marbles, they're not that. So in the back of your mind, you need to be thinking that this model that we draw, it's not totally correct, but we're going to get there and we're going to use it as we go. And then after that, we're going to solve some problems. We're going to talk about atomic number. We're going to talk about the mass number. We'll talk about what an isotope is, and we will go from there. All right. So simple picture of the atom. So simple picture. This is, I think, the older version of the fourth grade picture of what an atom is. So I'll put simple picture. Now this is not correct, okay? I'm not saying it's correct. I'm just saying it's useful to have in your mind, but as we go on, we're going to use more sophisticated version of this, okay? So let's talk about the helium atom, right? The helium atom. And so the helium atom is composed of 2 positive protons in the center and 2 neutrons. These are in the nucleus. The nucleus is very, very, very small. And surrounding that, we have the 2 electrons. So they have minus signs. And of course, the nucleus has, whoops, that's not a great circle. You have to envision that as being a nice circle there. So we're starting from the beginning, start pretending that you don't know anything, but I know that you all know that atoms have this thing in the middle called the nucleus. And the nucleus consists of positive charges called protons and other particles called a neutron that don't have any charge. That's why I don't have anything written there. So these are protons and neutrons, right? And surrounding that, in this picture, we have the 2 electrons which are orbiting around and around like a solar system, you know, going around the central nucleus, which would be like the sun. But again, in the back of your mind, neutrons and electrons and protons, they're not little balls. Electrons, we can rip out of atoms and do experiments with them. We've done many, many, many thousands of experiments over the last 100 and whatever years of physics and chemistry, and they are definitely not little balls with little minus signs inside of them. That's not what they are. They actually behave more like waves, almost like light is a wave and also has a particle character called a photon, that's light. Well, all matter, including electrons, have a particle nature, but also a wave-like nature. So in quantum mechanics, we model everything as a wave, and everything you've ever touched is actually a wave, including the protons and everything else. Everything has a wave-like character. But in this simple picture, it's useful to think of them as little balls because we can do a lot with that picture as far as visualizing how the electrons move around in a chemical reaction, how the atoms change position in a chemical reaction. So even though we know this picture is wrong, it is a very useful model, especially in the beginning of chemistry. But just know that when we get to more advanced lessons, we're going to throw this picture away and we're not going to consider electrons being a little ball. They're going to be a wave because to our current understanding, that's what they are. But for right now, the helium atom has 2 protons and 2 electrons there. And the protons are in the center with the neutrons, and they can comprise most of the mass of the atom. The electrons, if you remember from the previous lessons, they're very small in mass compared to the nucleus, to the protons. About almost 2,000 times less massive are the electrons. So the electrons have the same charge, opposite in sign to the protons, but they're not very massive at all. So when you look at this picture and you look at the idea that the nucleus is concentrated with the protons and the neutrons, then you understand why most of the mass of the atom is in the nucleus, in the center of the atom. Because surrounding that are these electrons that are, there's a lot of empty space with some electrons that don't have much mass at all. So the atoms, all of them on the periodic table, are almost all concentrated in terms of their mass in the center. Now it's natural to ask, all right, this is what an atom is made of. What are electrons made of? What are protons made of? What are neutrons made of? In our current understanding today, 2022, electrons are indivisible. That means we cannot break an electron up into a smaller thing. Now, 50 years from now, 100, 200 years from now, we may discover that's not true. But as our current understanding is, electrons, not very massive, they have a charge of -1, and you can't break them apart into anything further, right? However, the protons, which have a positive charge, and the neutrons, which have a neutral charge, these are, whoops, that was a terrible bracket. These are composed of quarks, I don't want to get into this because this gets into the realm of nuclear physics. Inside the nucleus, you break apart one of these protons, it actually consists of 3 different types of quarks. Or I shouldn't say 3 different types, 3 different quarks. And there are several different flavors and types of quarks. And the way that those 3 quarks are arranged, we call it a proton. And if you take 3 different quarks and arrange them in a different way, that's called a neutron. So the neutron has no charge, the proton has a positive charge. The charge character of those particles, it comes about because of the type of quarks and the arrangement of quarks that are inside. But I can't tell you that 3 quarks are inside of a proton and 3 quarks are inside of a neutron, and it's not the same exact amount of the quarks that are there. And so that again gets in the realm of nuclear physics. As in chemistry, we don't care about what a proton is made of because it's not involved in chemistry. In chemistry, we're looking at the whole atom. That's the nucleus, all of the electrons which surround it, how it reacts with another atom. How does it bond? Which means it shares electrons, right? Or maybe electrons get transferred from one thing to another, and then the atoms get rearranged. And so you might take sodium and chlorine, and then you put them together, a reaction happens, and they bond together, and we call that sodium chloride, right? But it's an electron transfer or an electron sharing. So what's going on in the center of the atom, as far as like how many quarks are in a neutron, it doesn't matter because it doesn't affect chemical reactions, okay, at all. But inside of a star, with nuclear fusion, or if you're doing nuclear fusion or fission reactors, or anything to do with breaking apart a nucleus, of course you have to know what's inside the protons and the neutrons, and all of that gets into modern physics, but it's beyond the scope of a chemistry class. So I said, again, all chemical behavior is due to electrons and indirectly the protons. So I guess I lied a little bit. The protons in the center, they do indirectly affect the chemistry. And here's why. Because when electrons move around, then you may leave behind, see, the atoms are neutral in the beginning because you always have in a neutral atom the equal number of protons in the center, there's 2 of them here, and electrons here, which are negative. And so if you have an atom like this and you look at it from a distance, you have +2 and -2, and so you have what we call electrically neutral atom. So that's why all the atoms around you, they don't appear to be charged because they have equal number of protons, which are positive, and electrons, which are negative. However, if you take an electron away, maybe it gets transferred to another atom somehow, and then you leave behind what we call an ion, which has a net positive charge. So we say that the protons and the nucleids don't affect chemistry, but they indirectly do, because as soon as you move electrons around and you have a net positive charge left behind, then that is what's going to govern how the reaction happens. So the protons do not come out and participate in the reaction, but when electrons get transferred and we have that net positive or negative charge of the atom left over as we transfer electrons around, then of course indirectly the nucleus does participate because it does have that positive charge, which is attracted to other things in the reaction, okay? So electrons govern what happens in the reaction, but protons of course govern things like electronegativity, how strongly an atom attracts electrons and things like that. Because the electrons in the center, or the protons in the center, are what are pulling those electrons in anyway. So indirectly, protons are important for chemistry, but we don't analyze protons in chemical reactions too much because they indirectly participate because they have a charged, positive charge. So let's talk about the size of this thing. So I drew a big picture up here. Let's talk about the size of the atom. Right? You probably already know this, but atoms are really, really, really small. So I'm going to draw the atom as just a circle here, even though we know it's multiple neutrons and protons. So I'm going to call this the nucleus, not the nucleus, the nucleus. Right? And around that, I'm going to draw a little dotted line, or a little dotted circle, I should say, which governs the boundary of the atom. Now, it's a little fuzzy where the boundary of the atom is because basically the size of the atom is where the outermost electron lives, the maximum distance where the outermost electron lives. But as we get into this more, you're going to realize that that's a little bit of a fuzzy boundary. All right, electrons don't have to be exactly here. It's a little bit of a fuzzy thing, but still, you can define where the bulk of the electrons reside in an atom, and you can call that the boundary. Okay, so this dotted line is supposed to signify where inside of this high probability all of the electrons and of course the nucleus resides. And what we figure out from this thing, that the size of this atom from edge to edge of what we're calling the boundary of where all the electrons live that surround the atom is somewhere in the neighborhood of 1 to 5, and we have a new unit I'm going to introduce to you called the angstrom. It's an A with an O on top, with a little O on top. 1 to 5 angstroms. You're like, what's an angstrom? Well, an angstrom, 1 angstrom, is a useful unit in chemistry and in physics. It's equal to 10 to the minus 10 meters. All right, so if you think of 10 to the minus 9 being a billionth of a meter, then an angstrom, 10 to the minus 10, is actually 10 times less than even that. So if you think about it, it's smaller, much smaller than 1 billionth of a meter, right? That's incredibly small. And that is the size of the entire atom. The nucleus is actually way smaller than that. So if we go and take a look at that, the nucleus here, I'll kind of put some arrows here illustrating the width of the nucleus, is on the order of, I'll put a little approximate equal signs, somewhere around 10 to the minus 4 angstroms. So the atom itself is incredibly small, 1 to 5 angstroms, where an angstrom is less than a billionth of a meter, but the nucleus is thousands of times smaller than even the size of the atom. Thousands of times smaller than the size of the atom. So a good way to visualize this is if you picture an American football field, or I guess a soccer field in other parts of the world, about 100 meters long, something like that. Roughly, okay? If you say that the size of the entire football field is the diameter of an atom, the whole atom is the entire football field, then the nucleus, where all the protons and all the not the electrons, the protons and the neutrons, where all of that stuff lives, all of this stuff up here, is right in the center of that football field, and it's about the size of a marble. That's about the size of my thumb. So envision in your mind how large a football field would be. That would be the width, the diameter of an atom. Right in the middle, the width of my thumb or a marble, that is the size of the entire nucleus. So when we say that an atom is mostly empty space, we really mean it. We mean that the concentrated charge with the protons and of course the neutral neutrons in the center is incredibly small. It's thousands of times smaller than the diameter of an atom. Right? Now, of course, you have smaller atoms and larger atoms because as you go down the periodic table, you're adding protons and electrons and neutrons, and the atoms are getting bigger. Okay, the smallest atom is going to be around here, around 1 angstrom, right? But actually, to give you a just another concrete example, chlorine, right, is approximately 2 angstroms in diameter as far as the atom, which is 2 times 10 to the negative 10 meters. Because it's an angstrom is 10 to the minus 10. This is double that, 2 times 10 to the minus 10 meters. And this is the diameter of a chlorine atom. So these things are incredibly small. Very, very, very inconceivably small. I mean, we could write the number down, but really it's impossible for us to really imagine, what the diameter of this thing is. It's just too small and removed from our everyday observation. And that's just the size of the atom. The nucleus, I've drawn it like this. It doesn't look that small, but it's 10 to the minus 4. That's 10,000 times smaller than the atom is. You wouldn't even see it. If you could hold the atom in front of you, you wouldn't even be able to see it as a dot there. So it is incredibly, incredibly small. Now, we're going to talk in just a second about some things that we need to talk about, the atomic number and the mass number and things like that, and talk about isotopes, very practical chemical things. But while we are talking about it, since the title of this thing is called Modern Atomic Structure, and we're talking about how the atom is constructed, I'm going to give you a little bit, which I did in the last lesson too, but we'll do it again here. We'll talk a little bit more about why this picture is wrong, okay? This picture leads you to believe that you have a concentrated nucleus, you have 2 balls which have little negative signs on there, and they just go around and around like planets in a solar system. In fact, the early models of the atom really did the calculations of the electrons moving as planets moving in a circle. And you can actually get pretty far, you can learn a lot from using that model, but as we learn more about what electrons are, they're not little balls and they don't move in little circles like this. So here's the little secret that I want to tell you in the beginning. You need to use this model of an atom with the nucleus and the electrons and the orbiting. You need to use them because to talk about how the electrons fill up around the atom, it's a useful picture. To talk about electrons jumping from one atom to another, it's a useful picture. But in reality, electrons are not little balls. They're actually, as far as our modern theories show, they're waves, or at least they can be modeled by waves, and they very accurately obey wave mechanics. You may have heard this term called quantum mechanics. It's a wave theory. Quantum mechanics is a wave theory. So I want to go on an aside with you and just tell you that there's been many experiments done with light, all the light hitting me. And people wondered, what is light? You might say, what does this have to do with chemistry? Just hang in there. I promise we're going to get back to where we need to go. But light's important. What is light? People figured out that light is a wave, right? Because when we do experiments with light, we can make the light waves interfere with each other. If you look at water waves, and when water waves go and hit two slits, you can actually see the water coming on the other side of the splits. They can interfere with each other. And what I mean by interfere is you have if it's a wave, you have a crest and a trough, right? And if you have two waves colliding, then they add together and the crest might get bigger and the trough might get deeper because they add together. So when you send light through tiny little slits, they interfere with each other on a screen, and you can see the light and the dark patterns of interference on the screen. So we know that light has a wave character to it. But then later on, when people discovered, like Einstein and other people discovered more of what light really was, and as we learned about quantum mechanics and did a lot of experiments with light, we learned that even though light has a wave character, it also has a particle character because it only comes in chunks. Like if you think of a wave at the beach, the wave is this very big, broad, spread out thing, and I can have big waves and small waves and medium waves. I can have a wave of any size I want. And that's how they thought light was too. You could have an intensity of light of any size. But as we did experiments, we figured out that light doesn't behave like that. It does have a wave character, but you cannot just have any amplitude or size of the wave. It only comes in chunks, and we call that chunk a photon. So you may have heard that word, a photon of light. A photon is a little packet of energy. We know it has a wave-like character because it's got a wave-like character to it, but it comes in almost like a stream of particles, which are called photons. So for a long time, people said, well, a light can behave as a wave, but it also has a particle-like character. Wave, particle, wave, particle. They kind of have to coexist when we talk about waves. Then later on, people started doing experiments with electrons and with matter. And they figured out that even though electrons are particles and we can shoot them, like little bullets out of a gun, right? We can measure when the particle goes by. We also discovered that electrons have wave-like character too. In fact, if you take those electrons and send them through a double slit, just like light, they actually interfere with each other on the other side of the slits, just like light does. You can see the light and the dark patterns of the electrons interfering with themselves as they go through the slits. And so what is it? What is an electron? Is it a wave? Is it a particle? Well, it is a wave. It's a wave-like structure. It obeys wave mechanics just like light does, but it has a particle-like character. We see that in terms of what we call the electron, okay? But then when you start to consider electrons being waves, then you have to talk about everything else. What about protons? What about neutrons? Well, it turns out everything's made of waves. That's our modern theory. Everything. Protons, neutrons, quarks, everything is made of waves, right? It's just that atoms are so incredibly small and the waves are so small, we don't notice the wave-like character of electrons until we can remove a single electron out and do experiments with it. Then we notice the wave-like character. Now, why am I telling you all this? Because we draw this picture and we draw little balls, and it imprints in your brain that these are balls that just go around and around like little marbles. And so later on, when I tell you that it's not that way, you have to unlearn all of that. So I'm not telling you to unlearn it. I'm saying keep this in your mind. It's a good picture. We will use it. I will draw this picture and we will use it. But in the back of your mind, I want you to remember that electrons are not balls. They're waves. And let me show you just one little picture before we move on of what I'm talking about here. So here you have a proton, here you have another proton, here's a neutron, here's a neutron. Instead of thinking about this electron being a ball that goes around, think of it as a wave that exists some distance away. And it is literally waving around here, and it connects back on itself so that it forms what we call a standing wave pattern all the way around. Now I've drawn it like a blob here, but you need to envision these things going do 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 do. It's like vibrating like a drum going back and forth. in time, right? If you imagine taking a string and tying the string to the wall and vibrating it, you can set up the waves on the string, and you can see them going do 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 like this, okay? Well, the electrons are behaving the same way. They're forming standing waves around the atom. So this is an electron. If I ask you, where's the electron? Where is it? Is it here? Is it here? Is it here? Is it here? No, it's everywhere, because the electron is not a thing that exists at one place. What happens is when we measure its location, yes, we measure where it is. But if you measure it a split second later, then it might be in another location. We measure it again, we're going to measure it in another location. Every time you measure it, what we say is the wave function returns a result to you and tells you where you found the electron that time. But the wave function is a probability wave. So every time you measure it, you're going to get a different result, but it does tell you where you are most likely to find the electron. Okay, if I have an atom here, I'm very likely to find the electron around the atom. I'm also quite possible to find the electron 10 meters away, but it's very unlikely. It's much more likely to be located around the nucleus of the atom. All right, and I'll just close this little part by saying something. I'll draw it again. You might say, why is he doing this again? We just did this in the last lesson. Well, because these are deep topics, and it takes a little while for it to bake in the oven. So this is a simple graph, we'll get to more of them later, that tells you the probability of finding an electron some distance away from the nucleus. So the nucleus is right here, nucleus. And it turns out that this, for hydrogen, looks something like this. It goes up, and then it goes down, and it tails off like this. So what this is telling me is it's very, very unlikely to find an electron. The probability of finding an electron at the nucleus is very low. It's not zero, though, but it's very low. And then as I go away from the nucleus, the probability peaks right around here. And this is the most likely place, right around here. This is the most likely radius that I'm going to find an electron surrounding a hydrogen atom, right? But as I go farther away, of course, the probability tails off. But notice that this probability never gets to zero. It is some tiny, tiny probability that I will find the electron around this atom 16 meters over there. So where is the electron? It doesn't make sense to ask where the electron is. When you're not measuring its location, it exists as a wave function with a probability of being in any point in space. There's a probability of it being in the nucleus. There's a probability of it being here. There's a very likely probability of it being a certain distance away, which we call the orbital radius of the electron. That corresponds to how far away it is in this picture. But it can be farther away from that with a lower and lower probability. And if you go 10 million light years away, there's a small chance that it's over there. But it's incredibly small. You might have to wait, 10 trillion years to ever measure the electron across the universe. But it is possible, right? So why am I telling you all these things? Because when we start in the beginning of chemistry, I want you to have this picture. I want you to picture protons and neutrons here and electrons which are orbiting around. But I don't want you to believe this too much. The electrons do not stay confined to a tight orbit. They can be closer to the nucleus. They can be farther away from the nucleus. They can overlap with each other, and they can do other crazy weird things that we don't think make sense because we're not familiar enough with quantum mechanics on an everyday basis. So electrons are wave, they're vibrating structures around here, and they have this mathematical thing in quantum mechanics that can tell us where the electron is every time we measure it. And we're most likely to have it measured a certain fixed distance away. And as we add more and more electrons to the atom, of course, they have to be farther and farther away, corresponding to the orbits, the orbitals that we'll talk about later. All right, getting back to the core of this lesson, we need to talk about atoms, which is what we've been talking about the whole time. But I want to make sure you understand that atoms are neutral. And when I say neutral, I mean that they are electrically neutral. This atom has 2 protons and 2 electrons. So from a faraway distance, if you stand back, it has a charge of +2 and a charge of -2. And when you add those all together, the overall charge of that atom is 0. When you stand far away from an atom, even the atoms in my skin, they all have equal number of protons and electrons. And because of that, they're neutral. So equal number protons and electrons. And that is why they are neutral. However, you can take an atom and you can create a charged version of it called an ion. You may have heard of ion thruster, ion drive, or just ions. Ions have a net charge. Whereas atoms are always neutral, ions can have negative charge, and this is going to play into chemistry quite a bit. So here's an example. If I have 2 protons and only 1 electron, see, it's unbalanced now, because in the atom, it's equal numbers, and so they're 0. But what would happen in this case? Basically, what you would have is 2 protons right here and only 1 electron. Of course, there could be some neutrons there too. We'll talk about that later. So you see, from a distance, you have an overall charge of positive 1, right? So the net charge is equal to plus 1, right? Because, or I guess normally you put the plus sign on the other side of the number 1, usually. Because you have a positive 2 and negative 1, and when you add those up, you get a charge, an ion charge of positive 1. So if you have an atom and you take away an electron, it's now called an ion, and it has an overall charge of positive 1. You can have another example of, let's call it 2 protons and 3 electrons. So again, they're unbalanced, right? But in this case, what's going to happen? You're going to have a situation with 2 protons. We can give our neutrons there if we want to. And then we have 1, 2, 3 electrons, which are all negative. And of course, they're orbiting. And of course, they don't orbit like this, but we use this picture because it's helpful, right? And we go over here and we say, well, what's the net charge? Well, we have a positive 2 and we have a negative 3. So the charge on this ion is negative 1. So 1, the little minus sign there, means negative 1 there. Because we have a negative 3 here and a positive 2 here, so we have negative 3, positive 2, you get an overall charge of negative 1. So this is how chemistry is going to work, and we're going to talk about this a lot. But when electrons get transferred from one thing to another, you might have some ions left over. And those ions, it's just a word that means charged atom, right? In regular atoms, there's no overall net charge, but ions definitely do have an overall charge. All right, so now we want to talk about zooming in a little bit more on the protons and neutrons and the electrons, and we're going to talk about their charge and we want to talk about their mass. All right, we learned in the last lesson, so I will say recall. We learned a couple of things. We learned that the electron has a charge. And in the units that we talked about in the last lesson, it was negative 1.602 times 10 to the minus 19, and it was a unit, an SI unit called coulombs. But notice this is a really tiny number. Why? Because an electron is a really tiny thing, right? You don't usually encounter one single electron, but I mean, that is the charge on the electron. Protons have a charge of what? Positive 1.602 times 10 to the negative 19 coulombs. Now notice, first of all, that these are exactly the same. It's not that they're close. They're exactly the same. It's kind of a mystery. We don't know why yet, but protons and electrons have the same charge, exactly. And they're not a little bit close, they're the same charge, equal and opposite. One has a positive and one has a negative. That is what allows the atoms to be exactly electrically neutral. If they were a little bit different, they wouldn't be neutral, but they are exactly the same, so atoms are neutral. All right? Now, the masses of these things, the masses of electrons and protons are tiny. So tiny, I'm not even going to write them on the board. The mass of an electron in kilograms is something like 10 to the minus 31 kilogram. They're very small numbers. So in chemistry, we don't really usually use the mass of electrons and protons in grams and kilograms. We have a new unit that we use in chemistry called the atomic mass unit. And that's what we're going to use here to talk about the masses of these electrons and protons, the atomic mass unit. So one thing we notice is that the masses of the electrons and the protons, they're tiny. The charges on the electrons and protons are also tiny. So what we're going to do is we're going to take this number here, this really tiny number, we're going to call it a new thing. We're going to call it the electronic charge. Because it would be really inconvenient to write this small number down over and over again. Same for the masses. So what we do is we say that the electron has a charge. This is really the number, but we just say that this is in units of what we call the electronic charge, this is -1. And in units of electronic charge, this is +1. We just basically say, hey, this number is really small. We're just going to call it 1. We're going to call the positive version of this 1, a charge of 1. Instead of saying 1 point whatever times 10 to the minus 19 coulombs, we're going to call that 1. And so protons have +1 charge and electrons have -1 charge. And that's going to be good enough for us because we don't care about the decimals. We just care about the imbalance between the protons and the electrons. And so we're just going to call this a charge of 1. All right, so we can make a little table here and we can say, all right, let's talk about protons. Let's talk about neutrons. And let's talk about electrons. And let's talk about their charge, right? And let's talk about their mass. But in their mass, again, the same problem. We don't want to talk about kilograms or grams because they're so tiny. We have a new mass called the atomic mass unit, AMU. And we're going to talk about that in this lesson, and we're going to talk about the AMU in the next lesson also. But what we know is that as far as the charge goes, the neutron has a 0 charge, right? 0 charge. The proton, we say, has a positive 1 charge, and the electron has a negative 1 charge. Normally, we write the charge after the number instead of in front, like in algebra, but it really doesn't matter. You can put it in front if you really want to. And so we can just easily see that these balance each other out. It's way easier than looking at these tiny numbers with all the decimals, and all we need to know is that they're equal and opposite, so we just rename it here. And then we have their mass. Now again, their mass you can measure in grams, but because we're talking about atoms and we're writing incredibly small numbers, we define something called atomic mass unit. I'm going to write these numbers down. The mass of a proton in atomic mass units is 1.0073 AMU. I'm going to talk about these numbers in a second. The mass of the neutron is 1.0087 atomic mass units. And the mass of the electron is, wait for it, 5.486 times 10 to the minus 4 AMU. Now, the first thing I want you to notice is that the mass of the proton and the mass of the neutron are almost exactly the same. I mean, to 3 decimal places, they're identical. Now, they're not really identical. They're different. And that is related to the quarks that are inside, that comprise the proton and the neutron. We're not going to talk about that, why they're different, but they're very slightly different. But they're also very close in mass, okay? But the electron is way different in mass. This is 10 to the minus 4. That's like almost 10,000, that's a couple thousand times smaller than the mass of these guys here. So the electron, a couple thousand times, thousands of times smaller in mass than the proton and the neutron, but the neutron and the proton are, of course, similar in their mass. And that's why we say that the nucleus contains virtually all the mass of the atom. Basically, you can ignore the mass of the electron completely when you're just trying to figure out the mass of an atom. Just ignore the electron. It's thousands of times smaller. It's not going to contribute. Now, the charge on the electron is very important. That balances the proton, equal and opposite, but the mass is completely different. Okay? Now, the obvious question that you should be asking yourself is, why is the mass of the proton not exactly 1? Why don't we just say the mass of the proton is 1 AMU? Or maybe we said the mass of the neutron is 1 AMU and everything else is in terms of that. Instead, we say 1.0073 AMU. Well, there's a story behind that, and I can't tell you that story now. I'm going to save that story for the next lesson because there's a little more to it that will take more than a couple minutes, and it will derail where what we need to cover here. But just suffice to say that in your mind, when you think about the mass of an atom, you can think of the proton and the neutron being roughly equal mass and roughly 1 atomic mass unit. That's what I do. I just think they're both roughly 1 AMU. Okay, they're both about the same. They're slightly different, but I don't care for most calculations. And they're about 1 atomic mass unit. And what is an atomic mass unit, by the way? 1 AMU is equal to 1.66054 times 10 to the negative 24 grams. And this is why we don't want to use the unit of grams when we're talking about the mass of individual protons or neutrons, because it's a tiny number and it got a lot of decimals here. So instead, we're just going to say, hey, this is roughly 1 AMU for the proton, roughly 1 AMU for the neutron. And the electron is way smaller than that. We can almost ignore its mass, usually, when we're talking about masses of items. Now, in the next topic that we do, we're going to talk a lot more about where this comes from, how it's defined. We're going to talk a little more about the atomic mass unit because I have a totally separate lesson on atomic mass. But for now, just know that these are the masses of the parts of the atom. Okay? Now what we have to do is talk about the atomic number and the mass number and the atomic number and the mass number and what an isotope is in chemistry. And then we're going to solve some problems to give you practice. All right, so the atomic number is just the number of protons that you have. So if I say I have a atomic number of 3, it just means I have 3 protons in the nucleus. If I tell you I have an atomic number of 10, I have 10 protons in the nucleus. That's all that this means. As you move down the periodic table, and we are going to pull the periodic table out in a little bit, as you move along the periodic table, the atomic number goes up by 1 each time because the character of the atom is governed essentially by the number of protons in the nucleus, and because the protons and the electrons that surround are equal and opposite, you always have the same number of electrons surrounding every atom. So if you know the atomic number is 5, then you know you have 5 protons, and then you also know you have 5 electrons surrounding because it has to be a neutral atom. Protons and electrons always are in balance, are always equal to each other for a neutral atom, all right? Now, you also have neutrons in the nucleus, so you could, but one thing I need to point out to you is you can have a different number of neutrons and still have the same element, and this is called an isotope. This is going to be very clear because I'm going to give you a concrete example in a second, but basically the character of the atom, for instance, carbon has a certain number of protons, oxygen has a certain number of protons, sulfur has a certain number of protons. That governs what element it is. But the number of neutrons can vary slightly. You can have some atoms with a little more or a little less neutrons, and so they're going to be more or less massive, but it will still be sulfur, or it will still be carbon. You probably heard of carbon-12, or carbon-14, or maybe some radioactive iodine with some, iodine, whatever, different isotope of iodine. These are just different flavors of the atom with slightly different amount of neutrons there, okay? So the way we write this down is, let's talk about the element carbon, and the way you would see it written down is with a 12 on the top, let's say, and a 6 on the bottom, all right? Now, the letter C is the symbol, which means carbon, obviously. And then this number down here, this is the atomic number. And what is the atomic number? That's just the number of protons. So that's just the number of protons. So you know right away that carbon has 6 protons. Every atom of carbon always has 6 protons. That's what makes it carbon, right? And because electrons and protons have to be in balance for every neutral atom, we also know that all carbon atoms, if they're neutral, unless they're in a reaction, they're always going to be neutral, they have 6 electrons also because they have to balance the number of protons that are in the nucleus. Then we put another number on top, and this thing is called the mass number. And the mass number is the protons plus the neutrons, right? That's why I say the protons plus the neutrons. So basically, you see this kind of thing written around in textbooks, and also you see it in scientific literature. Anytime you're talking about basically an atom, especially if it's an isotope, then you have the symbol that tells you what element you're talking about. This is the atomic number, which is 6. And when you look on the periodic table, you'll see carbon has an atomic number of 6. So all atoms of carbon have 6 protons. And then this is called a mass number, which is the addition of the protons, which is already written down here, plus the neutrons. So you can indirectly figure out how many neutrons this thing has, because if this number is protons plus neutrons, and this number is protons only, if you subtract them, 12 minus 6, it means you have 6 protons in this atom, okay? And 6 protons there. And you might see this written as carbon, and with a dash, and then the mass number up here, this is carbon-12. So this is the most common form of carbon. It's almost 99% of all carbon in the universe is carbon-12. And that's because it is more stable that way, essentially. So the number of protons determines what element it is. You always have to have the same number of electrons surrounding the nucleus as you have protons. The number of neutrons inside can vary, but you can always figure out the number of neutrons by subtracting what we call the mass number minus the atomic number. This particular atom would have 6 neutrons because 6 plus 6 is 12, or 12 minus 6 is 6. And you would call this carbon-12 because the mass number is 12. Now, there are other flavors of carbon, just like there are other flavors of hydrogen, like there are other flavors of helium. There's other flavors of every element on the periodic table. I think without any exception, there's always going to be a new flavor. And these flavors, we don't call them flavors, we call them isotopes. So when you see the word isotope, you need to replace it with the word flavor. So if I just told you there are 6 isotopes of sulfur in the universe, you would say there are 6 flavors of sulfur in the universe. They are all chemically the same. They react in the same way because they have the same number of protons and the same number of electrons surrounding. So they're going to chemically behave the same. The isotopes react the same, but they're different numbers of masses because they have different numbers of neutrons. And to illustrate that more, I want to do that down here. I want to write a table down for you. So what I'm going to do is I'm going to write down a couple of different types of carbon, or isotopes of carbon. So I'm going to put a carbon, we're going to put an 11 here and a 6 here. We're going to put a carbon, we're going to put a 12 here and a 6 here. We're going to put a carbon, we'll put a 13 here and a 6 here, and a carbon and a 14 and a 6 here. First thing you need to know is the bottom number is always the same, because this number comes directly from the periodic table. When you look up carbon, you'll always see the atomic number of 6. They all have 6 protons in the nucleus. Now let's go over here and let's ask ourselves, what are the number of protons in this thing? Let's look at what the number of electrons are in this isotope here. Let's look at the number of, I'm going to put N for neutrons, or I guess I'll put neutron here, number of neutrons here. And I'm going to say can write as here. And we'll understand this last column in just a second. Okay, so what did we figure out? Well, this is carbon, it's got 6 protons. The bottom number is always the atomic number, the number of protons. This is carbon, it's got 6 protons. This is carbon, it's got 6 protons. This is carbon. It has to have 6 protons because the element is basically defined by how many protons there are in the nucleus, the atomic number. So we always have 6 protons for all of these flavors of carbon, which, remember, flavor is a word that we use in our mind. We really are reading the word isotope. Isotopes of carbon, that's a flavor of carbon. It's like different kinds of ice cream. Slightly different, but they're all ice cream. They all melt. They're all made of milk, okay? So these are all having 6 protons. Now these are atoms of carbon. That means they're electrically neutral, and so they all have an equal number of electrons. So they all have 6 electrons. You have to have an equal and opposite number of electrons to protons in order to have a neutral atom. So we know already how many electrons are in each of these atoms as well. Now let's see how many neutrons are here. Well, we have a mass number, the top number of, in this case, 11. Now what is 11 minus 6? 11 minus 6 is 5, so that means there has to be 5 neutrons here because the protons plus the neutrons, 6 plus 5, is equal to 11. Now here we subtract 12 minus 6, there's 6 neutrons here. Here we subtract 13 minus 6, there's 7 neutrons there. Here we subtract 14 minus 6, so we have 8 neutrons right here. So what do you notice in this table? What you should notice that all of these carbons, these flavors, these isotopes of carbon, they're all exactly the same chemically because they all have the same number of protons in the center and they all have the same number of electrons. That means that when all of these flavors of carbon react with anything else, they transfer electrons, they bond, they all behave the same because they have the same number of protons and electrons. So they all chemically react the same. The only difference between them is that this one has only 5 neutrons and this one has 8 neutrons, and then you have all these in the middle. So what does this mean? Remember, as far as the atomic masses go, right, the protons and the neutrons are basically in your mind about 1 atomic mass unit. The electrons are totally negligible. They don't have any mass. So what this means is that this carbon has fewer neutrons and this carbon has more neutrons. They all have the same number of protons. The electrons don't matter for mass at all. What it means is that this is a very light, less massive version of carbon, and this one is almost double the amount of mass. It's a heavier version of carbon, all right? And that's why we call this the mass number, because it's proton plus neutron. So the bigger this number is, the more mass, because the protons and the neutrons contain almost all the mass. And so the higher that number, the more massive that flavor, that isotope of carbon or whatever it is. But chemically, they're going to react the same. And they're going to have many of the same properties, electrical conductivity, all these things, because the electrons and the protons are the same. The only real difference is that one will be heavier than another, okay? And heavier by quite a bit, actually, because if you look at the number of neutrons going from 5 to 8, you can see here, this is going from a mass number of 11 to a mass number of 14. So that's an increase of close to 50%. I think I may have said it would double in mass, but it goes from a mass number of 11 to a mass number of 14. So that's closer to a 50% increase. But anyway, it's significantly heavier than the lighter version of it. Now I put a table here, or column here that I can say you can write it as. So when you start writing these things over and over again, writing the 6 down here is kind of silly because carbon, when you look on the periodic table, it has an atomic number of 6. That's the big number written in the center, 6 protons. So you don't really need to write the number 6. If you're writing down that it's carbon, you already know from the periodic table that they all have 6 protons. So really, I can just write this as a C with an 11 up here, and I can just drop the 6. I can write this C with a 12 up here. I can write this C with a 13 up here. I can write this C as a 14 up here. And I don't really need to write the 6 because since I know it's carbon, and I can look up the atomic number of carbon, and I know that there's an invisible 6 here because it's all carbon, then I don't need to write that. So you might see it written like this. These are different isotopes of carbon, but you might see it without this bottom number here, but that's not a typo. It's just because you already know what it is. All right, now let me point out a couple of things. This one, we already said, you write this as carbon 12. You may have heard of carbon 12 just in conversation, right? Now this one's very important also. You write this one as carbon -14. So it's the name of the element with the mass number after it. Carbon 14, carbon 12. So what this tells you, this is carbon 11, this is carbon 13. And you write the different flavors of carbon in words as the symbol or the name of the element with the mass number after it. And you know immediately that carbon 14 is much heavier or more massive than carbon 12. Now, I'm not going to get into a bunch of data, but I will tell you that carbon 12 is by far the most abundant form of carbon in the universe. It's something almost 99% of all the carbon that you would ever find is carbon 12. So what I mean by that is if you go into a mine and you just dig out a metric ton of carbon and you analyzed exactly what isotopes were naturally mixed in there, you would find that about 99% of it is carbon 12, which means they would have 6 protons and 6 neutrons and 6 electrons, 6, 6, and 6 like this. But a small fraction would actually be carbon 12, which is the exact same thing with 1 less neutron. A small fraction you would find is carbon 13, which is the same thing as carbon 12, but with 1 extra neutron. It's a little heavier, but electrically it behaves the same. Chemically it behaves the same. And you would also find that there's a very small chance, a very small fraction of a percentage that you can encounter carbon 14 out of your sample that comes out of the Earth. And that's exactly the same thing as the highest abundance carbon 12, but with just 2 extra neutrons added in the nucleus, carbon 14. Now, you might say, well, at least I personally think you should ask, or well, the first thing I asked is, well, why can't I make a really heavy version of carbon? Here I have a carbon a carbon 11, a carbon 12, a carbon 13, a carbon 14. Let's make a carbon 15. Let's make a carbon 16. Let's just ram some more neutrons in there, make a carbon 18, carbon 20. Let's make a super heavy version of carbon 100, where it's got 6 protons, and then 94 neutrons or whatever for a total when you add them up of 100, carbon 100. Well, nature doesn't work like that. You can't do that. And it comes down to the little silly little version of the atom that we all learned when we're in 4th grade that I told you is useful to think about. And here's what we're going to do. The way this works is you have positive charges right here. Positive charges. They want to repel each other. But the nucleus stays together. It's very small, it's tightly bound, and obviously the nucleus isn't flying apart. So how is it possible that these positive charges are right next to each other? If they're trying to repel, how is that possible? I mentioned it in the last lesson, but that's because there's another force of nature called the strong nuclear force. It's actually much, much stronger than the electric repulsion going on here, but the strong nuclear force, it only acts over incredibly small distances inside the nucleus of the atom. Outside of these distances of the nucleus, the strong force goes to 0. But inside the nucleus of the atom, the strong force is much, much stronger than the electric repulsion. So the strong force can hold it together. Even though the repulsion is happening between the protons, the strong force overcomes it. Now, what happens when you add a neutron? So what's going to happen? So this is a very stable form. when you have the neutrons there and the protons there, and the way the strong force works, because you have to have mass for the strong force to work, the neutrons facilitate the strong force as well, and they're all kind of bound together with that strong force, okay? Now, let's say you add another neutron. Okay, so now the nucleus is a little bit bigger, but the strong force can still hold it together. Now you add another neutron. Now you have 2 extra neutrons in there, and the nucleus is physically larger than it was before. Well, now the nucleus starts to become unstable, because as you made the nucleus bigger, the strong force is having a much harder time holding it together. Okay, it's having a much harder time holding it together, and that means that periodically this nucleus is going to decay. And if you make very heavy atoms like uranium or plutonium or anything like radium, anything radioactive, the reason they're radioactive is because the nucleus is so big that the strong force can't hold it very well. And so it decays and it shoots out radiation. The radiation can be neutrons flying out. The radiation can be other decay products coming out. But they're happening because the strong force can't hold it together anymore. So this is why this one is the most stable, because the way the strong force works, it's maximum strength when you have 6 protons and 6 neutrons there in close proximity. When you start adding neutrons, the strong force, because the thing's getting bigger, it's having a harder time holding it together. And so eventually you get to something like carbon-14, which actually is radioactive itself. Carbon-14, I looked it up, it has a half-life of 5,730 years. That means if I have a bucket of carbon-14, the radioactive version of carbon, it's going to look like carbon, it's going to smell like carbon, it's going to react like carbon, it's going to behave like carbon, but it's going to be radioactive. It's going to decay over time into something else because the nucleus is just a little bit too big for that strong force that's acting at that level, and so it decays. And for those of you who are curious, I was curious about this myself, so I looked it up. What happens here is you have some extra neutrons here, and it's having a hard time holding on to them. So what happens is one of these neutrons turns into a proton. It transmutes into a proton, right? And then also an electron comes out as well. And so basically what happens is the carbon-14, it basically turns into nitrogen-14. Because when you look on the periodic table, find carbon on the periodic table, atomic number 6. Well, what's one element over is atomic number 7 with 7 protons. That's nitrogen. So if you have one of these heavy carbons with 8 neutrons here, and one of these neutrons turns into a proton, now suddenly you have a new element entirely, because you don't have 6 protons anymore, you have 7. And when you look on the periodic table, atomic number 7 is nitrogen. So this is nuclear process. This has nothing to do with chemistry and chemical reactions. I'm just telling you this because I want you to have a complete picture. I want you to understand as much as you can, as much as we all can. So if you start here, you have every element is going to have a most stable version of itself, where you have the number of protons and the neutrons, which are going to be similar, very close to being equal most of the time. And that's going to be what we call the element or the isotope with the highest abundance in nature. But you're going to have flavors, which we call isotopes, with more or less neutrons. Those isotopes will behave chemically exactly the same as the one that's most abundant, but it just may be heavier or lighter, more or less massive. And of course, you can't make it too massive, or else the thing just becomes radioactive, and carbon-14 is radioactive. We actually use carbon-14 for radiometric dating to see how old things are. That's another lesson for another day, but it has to do with living organisms incorporating carbon into their body, and we know how fast the carbon decays, carbon-14, and so we can tell the age of the organism because of how much carbon-14 is left in the sample after we dig it up, because it turns into something else, turns into nitrogen in this case. That's a lot of stuff, and I think we're going to stop it here. I would like you to watch this lesson a couple of times. I covered a lot of stuff. We have problems that we have to solve to get you comfortable with atomic number. The basic idea of this lesson, if we had to do a lightning round of just a very fast summary of what we did, we talked about the simple picture of the atom. We said we have a nucleus, we have electrons, we have an equal number of protons with the electrons. We also have these things called neutrons in the middle. We said that the electrons, as far as we know, are not divisible. They're not composed of anything smaller, but the protons and the neutrons are really made of smaller things called quarks, and we're still researching that in modern physics today. And then we said the boundary of what we call the atom is on the order of around an angstrom, up to maybe around 5 angstroms. An angstrom is 10 to the minus 10 meters, so 10 times smaller than a billionth of a meter. But the nucleus is thousands of times smaller than this atom. And we said that if the football field covered if an atom would just sit down in a football field from end to end, then the nucleus would be the size of a marble or the size of my thumb right in the center. Incredibly small here. Chlorine, we said, is about 2 angstroms in terms of its diameter. And then we said this model is useful, but really these electrons are not really balls that orbit like this. These electrons are really waves, and they're vibrating and waving around the atom. And then we said that this wave nature of the electron, it really tells us more about the probability of where we would find the electron if we measure it with a detector. And sometimes we're going to measure the electron very close to the nucleus, and sometimes we're going to measure the electron very far away from the nucleus. But most of the time, the highest probability is going to be at a distance away from the nucleus, which we call the orbital radius, which is what we're drawing in this picture. But the electron can be farther away or closer with less probability, of course, according to this. And all of this comes from a lot of math in what we call quantum mechanics, quantum chemistry. Then we said atoms are electrically neutral because they have equal and opposite protons and electrons. But if you take an electron away, or if you add an electron to a neutral atom, you're going to create what we call an ion. If you take an electron away, then you're going to have a net positive charge. If you add an electron, you're going to have a net negative charge. And once an atom becomes an ion and has a net positive or negative charge, the electric force takes over and wham, chemistry happens, because the electric force is so incredibly strong. That's what causes chemistry to happen, and so ions are a big part of that. Then we said that electrons and protons have equal and opposite charges down to the decimal place here, and the masses of these things are tiny, and we don't want to write these numbers down, so we create a new system. We say that protons are +1 in terms of this electronic charge number, +1. The electrons are exactly -1, and the neutrons have 0 charge. And then we said the masses, we don't want to write grams down or kilograms, so we invent a new unit called the atomic mass unit. The neutrons and the protons are almost exactly the same, very close to 1 AMU, but not quite. We're going to talk more about why they're not exactly 1 later, but here are the masses. The mass of the electron is basically negligible. It's very, very small compared to everything else. And then we talked about what an AMU was equal to. And then we said, well, we can have for the atomic number, that's the number of the protons. The electrons are going to balance that, but we can have a different amount of neutrons and have the same element, because the element character, what element you have, is governed by the number of protons you have, right? So for instance, for carbon-12, we said, we call it carbon-12, it has 6 protons, and therefore 6 electrons, and it has 6 neutrons, and so when you add the protons and the neutrons, you get something called the mass number here. And then we filled out this table basically showing you that all of these things are carbon. They all have 6 protons. That determines that they are carbon. They all have 6 electrons, so they're a neutral form of carbon. If you add or subtract an electron, you get an ion, a charged ion. We don't have that here. We have equal number of protons and electrons. And the neutrons is what is allowed to vary. We have a highest abundance version of every one of these isotopes for every element on the periodic table, and you can add or subtract neutrons and make a different flavor or an isotope of this thing, and they're going to be basically less abundant in nature. And of course, you can't make them infinitely big because the nucleus will fall apart and it's not stable at all. And so carbon-14, for instance, is radioactive. We talked about how that works. I'd like you to watch this a couple of times. I could have skipped over a lot of this stuff and just saved it for, like, I don't know, a few months from now, because a lot of it we won't use until later. But I also don't want to rob you in the beginning, rob you of learning something that is like a crowning achievement of humanity, to figure this out, that we can do experiments and learn what these things are made of. It's amazing what people have figured out, I guess is what I'm trying to say. So I don't want to hide it from you. I want to show it to you in all your glory, but take you through the journey so you know where we've been and where we're going. I'd like you to watch this again. When you feel like you get it, follow me on to the next lesson. We'll do some more problems involving the atomic number, and the mass number, and the isotopes of atoms. Learn anything at mathandscience.com.